All right, so again, this is 10.1. And it's essentially we're going to be talking about experimental and theoretical probability today. Just going to define those things and showing some of the examples that go along with them. But we need to know some terms first. So probability basic definitions, we got an outcome, right? An outcome is the possible result of a situation or experiment. Again, in probability, we seem to use a coin flip or the roll of a die a lot of times. So the two possible outcomes of flipping a coin would be heads and tails. Obviously, it depends on the situation when it comes to our different possible outcomes. An event may be a single outcome or a group of outcomes. So flipping the coin, that's an event. Right? We could say we flip 10 coins, right? And that could be one event. Flipping 10 coins could be one event that we're talking about. Like that's the group of outcomes that we're talking about. And our sample space is the set of all possible outcomes. Okay. So flipping a coin, our possible outcomes are heads, tails. We roll a die, our possible outcomes are 1, 2, 3, 4, 5, and 6. Okay. Those would be our sample spaces for the event of flipping a coin or rolling a die. Probability, a lot of times we shorten it instead of writing the probability of this happening. We write just a capital P, and then in parentheses, we put the event. So for flipping a coin, we could say like P heads. And that's basically asking what's the probability of hitting heads. Excuse me. So that's the shorthand way of writing it. Probability's definition is a numeric value from 0 to 1 that measures the likelihood of an event. We always measure it by the number of favorable outcomes over the number of possible outcomes. Now, we say 0 to 1, our probability, but a lot of times we use fractions that represent the numbers between 0 and 1 or percents. In probability, you hear a lot of things where it's like 50%. What's the probability? 50%. Well, 50% is equal to 0.5, right? So that's still a number between 0 and 1. Or what's the probability? It happens a quarter of the time, 1/4 of the time. That's still a number between 0 and 1. The numbers closer to 0 are outcomes that are less likely to happen. The outcomes closer to 1 are the ones that are more likely to happen. Again, you can write them as a fraction, decimal, or a percent, but all of them are equivalent numbers between 0 and 1. Kind of situational, depending on when you would use the ratio decimal or percent. I'll try and go at a pace of people are writing stuff down. You guys can you guys will have time to write down. Again, I will be sharing these blank slides with you after class, so you'll have access to these if you need to go back and look at them. So if you don't feel like you need to write everything down, that's okay. You can write maybe some of the parts that may just help you remember it. So that way you kind of compare your notes to the blank notes. A complement of an event. Okay, all the possible outcomes in the sample space that are not part of the event. Okay, so for instance, I could say something like, what's the probability of not rolling a 2? Okay.
It's 5, 6.
So it's the complement, so it's all the outcomes, the favorable outcomes in that case would be all the ones that are not 2, so that'd be 5 of the 6 bases. Okay. But this makes sense because when we talk about complementary angles, they're the 2 angles that when you add them together, they equal 90. So the complement, the complement, if you have an angle that's 50 degrees, the complement is 40, that brings it to 90. Okay. Same idea here, we're just looking at the 2 probabilities. The complementary probabilities are the ones that when you put them together, you get 1. All right. But we do a lot of some probabilities using these complements, okay? Yeah, I think it's a cool probability fact that if you're in a classroom, as long as there's at least 21 people in the classroom, then there's a better than 50% chance that 2 people in the classroom share the same birthday. Which is kind of a weird stat, but the way you actually figure that out is you actually use the complements. You're actually figuring out what's the probability that nobody in the classroom has the same birthday. And when you figure it out, it's less than 50%.
Well, like there's like for the second person, there's a 1 in 205 chance to have the same birthday.
Only if you have 2 people. You're only talking about.
And then after like more than that, like after that's just like when 2 people, and then
Yeah, it's just the probability. It just slowly.
it compounds.
Yep, and it's pretty cool. It's pretty, but the way you figure it out is actually using complement rather than trying to figure out what's the probability. It's actually a lot harder to figure it out from just figuring out what's the probability of 22 people having the same, 1 of 2 of them having the same birthday. It's harder that way. It's easier if you figure out what's the probability that they don't, and then you can subtract that from 1. Theoretical probability describes the likelihood of an event based on mathematical reasoning. So this is what most of the time, when you think about probability, you're probably thinking about theoretical probability. Okay, flipping a coin, rolling a die, picking a card out of a deck, like a specific card, you know, a 1 in 52 chance. This is all based on mathematical reasoning. Basically, there's no variability within our probabilities here when we're talking about flipping a coin. It's always 50%. Now, yeah, it could land on its side, but we're talking about coins that never land on its side. Okay. So with theoretical probability, you're talking about things that the probability doesn't vary. It's going to be the same probability every time you do that event. Experimental probability measures the likelihood of an event occurring based on actual results of an experiment. Okay, now this is where the probability is a little bit different. Okay, let's say that we did flip a coin, right? And we flipped the coin 10 times, and you got heads 4 times, you got tails 6 times. Well, our experimental probability tells us that number 1, it's not a fair coin. All right. And number 2, on your next flip, you'd be more likely to get tails.
Well, But it should be equal to.
Not right. I'm just explaining the difference between theoretical and experimental. Experimental probability is based on actual measures of results. Okay, so actual results. Now, flipping a coin, yes, if we were to do it for 1,000 times, it's probably gonna be really close to 50-50.
Well,
Alright.
it's still be uneven probably,
It might be uneven, but it should trend towards 50% each. Okay, but the experimental probability isn't gonna be exactly 50-50 probably, all right? Now, we use experimental probability with a lot of different things. Right, so there's a lot of different things that we can use it for that aren't just flipping a coin and rolling a die. They could be more real life type things. Somebody's batting average, right? That's experimental probability. Okay, that's telling you what the likelihood of them getting a hit on their next at bat based on all their previous at bats. Okay, it happens a lot in sports. And I think I tend to think about sports a lot of times, but we could also talk about people that work for insurance companies. They're definitely giving these ratings and these probability scores to drivers. And a lot of times it's based on other drivers that are similar to them and the number of accidents that they have. Right? That's kind of an experimental probability. It's taking the previous data and figuring out what the likelihood of the next event is going to be. All right. Sample space. Remember, our sample space is the possible outcomes. I want you guys go ahead and list on your paper the possible outcomes of rolling a regular 6-sided number cube or a die. Yeah, I don't know if there's like a trademark name on die. Probably not.
No. Well, like with trademarks, it's like they get too wide and trademarks and now like they can be narrow.
Yeah.
Like a regular, it's like the whole.
There isn't. I think it's just easier for people to say. It's a number cube. During non-COVID years, I usually have a bunch of puzzles all over the place, including like a couple decks of cards and a couple Rubik's cubes. But I can't find all, so I'll have to look. For the probability unit, cards are a good thing to have too. All right, so our sample space, this one's, we've talked about this, but it's just 1, 2, 3, 4, 5, 6. Okay. So our sample space is this set of numbers, 1 through 6. Okay. Now, we can use this sample space. Okay, I'll copy it up here. What's the probability of getting a 4?
Oh, I need
Dangerous out there?
to get my shield.
Like, what kind of a shield?
That thing.
This was like a
Uh,
crusade shield.
just get that now.
Yeah, you can do it.
All right.
So remember, probability is the number of favorable outcomes over the number of possible outcomes. So 4 is our favorable outcome over our possible number, so that'd be 1 out of 6. In this case, I would say a fraction is probably our best way to write this. what's the probability of getting an even number? Well, 2, 4, and 6, so 3. Okay, 3 out of 6, which is a 1/2. What's the probability of getting something less than 3? I know this is all pretty straightforward. 1, 2, there's 2 that are less than 3. So you have a 2 out of 6, which is a 1/3 probability. A number less than 3. Okay. Now this is all pretty straightforward when we're talking about like flipping a coin or rolling one die. When you start combining things, it gets a little bit more complicated. Okay. So here now we're rolling 2 regular 6-sided number cubes. Our sample space gets bigger, okay, because it's not just, now we have 2 separate cubes. I have a green and I have an orange cube. All right, so my sample space, I think I've got, yeah. So we can actually, it's actually a little bit easier to organize my sample space like this. Like every time I roll, we'll call this the green and this one's the orange. All right. Or if you want to say yellow cube or purple cube, that's fine too. So this is where I roll 1 with both of them. So it'll be and we'll make the going this way, that's the 1, going down, that's the second one. So 1, 1, this one would be 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Okay. Then everything 1, 2, 3, the numbers in front stay the same, but now I'm rolling a 2 on my orange cube. So 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. And this is tedious, but you have to do this sometimes in order to figure out your sample space, because we need to, if we want to know details about the sample space, all right, we need to know what the sample space looks like. And you'll see with some of the questions I'm gonna ask, they'd be hard to answer unless we had this list. Four, 3, 4, 6, 4. One, 6, 2, 6. All right. So there's our sample space where we've got all the different outcomes. Okay. Now let's see. Let me ask about this. What's the probability of getting a sum of 7? Okay. Now, if I just said you have 2 die, I said what's the probability of 7 getting a sum of 7? You'd have to think about it. Okay.
Well,
Now,
it's not that hard because there's whatever number you roll on the first, if you one number on the second dice will be equal. Have the first dice equal 7.
correct. You can say that about any number that you roll.
Well, but like you do 6 example.
What's the probability of rolling an 8? Is that gonna be 1 in 6 too?
No, it's I can calculate it on 5.
So, but I know what your brain's kind of doing is what we need to be doing. We need to think about what's the probability or probable, like our likely outcomes over the total outcomes. So for the probability for a sum of 7, we need to identify where the ones that are a sum of 7. Well, it actually falls, it ends up being those 6 all add up to 7. And there are 6 times 6, 36 total. So yes, it is going to be a 6 out of 36, which is a 1 in 6 chance of it being sum of 7. And that's why most dice games, like rolling a 7 is like that's like the winning thing a lot of times. Like craps, 7 is a good number to get.
Or something special like that. Like a robber instead of a 15.
What's the probability for a sum of 10? Okay, for the sum of 10, well, let's take a look at our sample space. 10, let's see, 4 and 6, 5 and 5, and 6 and 4. There's only three out of our 36. Which is a 1 in 12 chance. And then how about our one, a probability that's not a sum of 4? Well, sometimes in this case, what you want to do is figure out what the sum of 4, because in this case, the sum of 4 is going to be less than. So,
Well, the probability is 11 12.
these 3 add up to 4. So 3 out of 36 out of 4, how many of them don't add up to 4?
All the rest.
Should be 33 out of 36.
Yeah.
They're taking 3 away from 36. Which is an 11 12 chance. Okay. All right. Good. Let's look at an experimental probability situation. Okay, it says JJ makes 32 free throws and misses 28 free throws during one practice. How many free throws would you expect him to make in his next game if he takes 15 shots? Well, let's figure out what our experimental probability equals. So a number between 0 and 1. So it says he makes 32 and misses 28. So let's see, our favorable outcome is 32. Our sample space means that'd be the number of total free throws, the number of outcomes. We have to add 32 and 28, which would be 60. Okay, so 32 out of 60. Well, let's go ahead and reduce this. Good, because I'm just doing it in my head. I'm just going to split these in half. We get 16 and 30. Split in half again, 8, 15. So this is the experimental probability. Now, it just so happens that he takes 15 free throws next game, which doesn't always work out that way. But how many free throws would you expect him to make in the next game if he takes 15 shots? Well, what we can do is we can take our experimental probability, then we can multiply that times the number of shots. Because we're looking for this portion out of his total number of shots. Now, if he would have taken like 20 shots, then we would have ended up with some kind of decimal, and we'd have to then kind of round it to up or down, depending on the situation. But in this case, 8 15s times 15,
Shots.
where we would our best guess would be that he would make 8 shots based on the experimental probability. All right, that covers our notes for today with our theoretical and experimental probability. There is an assignment that I will pass along to you guys.